Let's do a little talking about capacitors. So this is right out of the Physics 2200 textbook. And although I chopped it down a lot, this was one of my 2200 lectures. And chopped it down a bit. Let's see. Make that now it's a little bigger. And you want to draw in case I want to write on it. Okay. Alright. And well, we don't need that. So this is the basic model of a capacitor. So you have, and in fact it works for all of them, and they mostly all actually look like this inside, although capacitors come in many shapes. And you see that there's the two plates, and you have a separation. You talk about the area of the plates, and there's a potential difference between them, and you talk about the Q of the plates. Now, the net Q is 0, but you always talk about the charge on a capacitor. So if you like, you just think about it's a positive Q. No one ever puts a sign on it. What the heck is that noise? And yeah, the separation, D. So we have Q and V and D and the area. And as always, V almost always means a delta V. And here they're calling it VAB. I suppose that's all right. We usually think of that as the terminal voltage. But this is labeled plate A and plate B. So the simple and, well, the mathematical expression for capacitance is the amount of charge that a capacitor can store, and how much voltage does it take to force that much Q in. And that's why the V is in the denominator, because if you need less voltage to get that Q, you think the voltage is, you think of as a force. And you want the capacitor to store charge. And in fact, at the end of the day, the capacitor is storing energy, and it's storing energy in an electric field. And you may recall from your 2200 type that electric field is equal to volts divided by distance, volts per meter. So you can kind of see where we're going to go with this. So the more Q I can store, the higher is my capacitance, and the less voltage I need to store that amount of Q also means a higher capacitance. And so I debated about keeping these slides. The electric field of an infinite plane, and one of the assumptions is that if you have the sides, A1, A2, for example, that A1 slash A2, or well, the way it's stated is D is much less than A1 or A2. So what that means is that, remember we said there's an electric field in here, and so by making the stipulation that the separation is small compared to the dimensions of the area, that means we can neglect the fringing effects. Because at the edges, the electric field is going to bend out. But with this condition, we can basically ignore that. That comes to mind because we're using the equation for an infinite plane. And you might say to yourself, yo, H, how can we use infinite plane? We don't have an infinitely large capacitor. but it's valid as long as D is small. So if you have two plates, because we need two plates because we can't have any net Q, we need two terminals for a useful device. So we just say that the E field is just the sum of the two plates, which is then sigma over, and sigma is the coulombs per unit area over the dielectric constant, which is actually the permittivity of free space, not a, it's the, it's the dielectric, we just define it, well, no, that's the permittivity of free space means what is the strength of electric field you get for a given amount of voltage. So sigma coulombs per area, Q over A. And so at the end of the day, this is the E field inside of our capacitor. And notice that the E field strength would get less for the same amount of Q if I increase the area. Where did you go, Mousy? There you are. What's next? So I also took this one further because we know that if E is equal to V over D, this is just generally true, and especially when you have parallel plates, this is a very simplistic equation then. Because with parallel plates, then if you may remember equal potential surfaces, you can just draw these out every so many volts, and it turns out that if they're equally distant in voltage in parallel plate, they're going to be equally distant in distance too, in centimeters. Is that all? Does that sound familiar to everybody? Okay. You initially learn E fields from Coulomb's law equal, oh, I forgot, KQ1, Q2 over R squared. And that units are newtons per meter. But for most of the time in the real world, you care about, newtons per coulomb. Shit, sorry. I'm thinking of the next sentence. You mostly think of volts per meter because a typical high-energy physics detector will have metal plates, one at 5,000 volts, one at 0. There'll be some kind of gas inside, and a particle will traverse the gas, leave a trail of electrons, and then the electric field collects them. And so you speak in terms of volts per meter. So this is always true, this equation, and I want to rearrange it a little bit and put it back into my capacitor equation, the E field in my capacitor, and I end up with this. So now we have VAB. This is the important thing to see. QD over epsilon 0A. And it should have all the same stuff on it, yeah. I picked those two out, and I can then say I now have two definitions for capacitance. One that deals with quantities I could measure with a voltmeter or an electrometer, and one that has to do with the physical characteristics. And the two of them are intertwined. And it falls out because of the geometry, parallel plate. So all capacitors, even those little yellow ones, inside that epoxy, that there are two metallic layers, and then there's a layer of ceramic in between them. And yeah, there's the summary. And it makes sense if you think about it. If the area is bigger, then I can store more Q. If I make D smaller, then if I make D smaller, then my voltage per meter goes up, my E field gets stronger. So what is that? Yeah, that one's always the hard one to think about. So making D smaller is akin to making the electric field stronger. And I've linked it into the module. These FET sims are really useful things. So if I have my battery here, and I can start increasing the voltage, you see that the charges build up. You see that the electric field builds up. And this thing is neat because I can change the separation. So the electric field is weaker now. I didn't change the voltage. The Q, the amount of charge will change. And then I can also change the area. And you see you have current flow. Now, an interesting thing is that if I disconnect the battery, then you'll notice that the amount of Q doesn't change. And the amount of stored energy changes because the electric field strength changes. Now if I switch it back, so what happens is with no battery, Q is a constant. With the battery, V is a constant. And that's not a big deal for us. That's more of a big deal for solving problems in Physics 2200. But definitely you should play with this. One neat thing is the light. So we charge the capacitor, and then it stays there, and now we connect it to the light bulb, and we see that the light bulb gets bright, but it dims out. So this is so-called time domain also. And that's the first thing we're going to study, is the time domain, and we're going to do something like this. It's too bad they should have the light bulb connected all the time, because we'd see that it'll turn on in a similar fashion. Actually, what will happen is if I had a light bulb, the light bulb would turn on very brightly, but then as the capacitor fills up, it would get dimmer and dimmer. We'll talk about that now. So capacitors come in all shapes and sizes. These ones here are, we have some examples. This big one could be a 1 centimeter. And you notice this one here, and if you're into subwoofers, that's what that is. That's a subwoofer capacitor. It's interesting. It says 1.5 farads, right? When I started master's program in 1990, I noticed outside of a lab this thing being put for garbage. And it had all these warning signs on it, and it was about the size of a treasure chest. it was metal, heavy metal, and had these lifting shackles on it, so it must have been very heavy. And it was a 1 farad capacitor, right? And now look at that. That one in that picture is 1.5 farads. Over in the 2200 activity, they have now these little tiny guys that are 2 farads. And it has to do with material science, what they put in between the parallel plates. It's amazing to me. I would have never thought you could make a full farad capacitor any smaller than what that person holding it in their hand right there. Let me see. I'm missing the picture. Oh, okay. Here we go. So basically, you have, in the case of the capacitors that look like that, you have 2 pieces of foil, and then you would look in there, you'd see this waxy paper, and that's dielectric. Here it says plastic. Yeah, nowadays, who knows? When I was your age, it was this waxy paper, which had PCBs in it, right? Those are all gone now because that's cancer causing. But as long as you didn't cut them open, you weren't exposed to it. Okay, so I'm not going to derive it right now. There's rules of combination. They're opposite of resistors. So these are, I'm a little upset with myself. I don't have the picture anymore. But it's not the emphasis of chapter 2. In parallel, they add linearly without the inverse. The way to think about it is when they're in parallel, you're just increasing the plate area. When we look at inductors, I'm going to show you how when you do impedances, so in parallel, impedances add up like this. So I'll give you a little taste. But remember, the capacitor is 1 over 2 pi Fc. So if I do 1 over that, you notice that I would get 2 pi Fc total equals 2 pi, and I'll just pull that out, C1 plus C2 plus C3, right? Isn't that neat? So I haven't violated anything. All the math is consistent. But most times, in 2200, there's a derivation that's done a little differently to get this kind of rule of combination. For us, we really aren't going to deal with these too much. Because it turns out, one of the first things I learned in graduate school was I saw this circuit, and the circuit had this section that had a power supply, and then it went into the amplifier that I was working on. And then I saw 2 capacitors, 1, 2. And one capacitor was 1 microfarad, and one was 0.1 microfarad. So, of course, the first thing I said to the engineer helping me is, why not just use 1.1? Because it turns out in the real world, the 1 microfarad capacitor look like this, because these work best at low frequency. And the 0.1 microfarad was one of those little yellow guys we use. They work better at high frequencies. So that's why you needed 2 separate ones. And what those did, they took away the ripple. Remember when in the oscilloscope lab we were looking for ripple on the power supply? And they get rid of it by capacitors. In fact, in chapter 3 we're going to create a power supply, and we're going to examine that ripple and how the capacitor deals with it. We're not going to go to this level of nuance until we start wiring up our little chips, and then we'll start putting, these are called decoupling capacitors. And so if you have a very sensitive circuit, and it could be that the little bit of ripple will screw it up. So you have these caps. If you look inside any circuit boards now, or if you look at a computer motherboard, the CPU, there's these little tombstone-y things. They're all capacitors, and they're all there to get rid of ripples, because you want the square pulses to come through, the ones and zeros to come in without noise. Okay, what do we have here? So this is important. We want to understand. It's a basis for trying to understand what we see in the time domain. So we have this equation here. Remember, it's C equals Q over V. But this is what's so-called steady state. We've connected a battery, and we waited till the end of the day to make sure the capacitor is full. There's no more current flow. Steady state. But of course, capacitors aren't very useful in DC circuits. They're never used in DC circuits. So notice now we have a little v and a little q, and the implication is that they're time dependent. Whenever you do derivations, especially in these engineering type derivations, you just don't want to constantly write q of t or v of t. So we say that at any instant in time, whatever voltage there might be, there's going to be some Q that's less than the big Q, and the relationship between them is determined by the capacitance. So I remind you that work is in joules, and if I do joules per coulomb, that becomes volts. So joules per coulomb is also aka volts. So that's what changing a voltage, you're adding energy to the electrons. That's what it is. When you say I have a battery provides energy. So for every coulomb of charge, it produces that. If you multiply volts times coulombs, you get joules. Hopefully that came out of your physics part 2. I don't know if it did or not. So we can think of work as Q times the voltage. So we can construct this differential here, that if we want to add a little bit of charge at a particular voltage, we assume the voltage stays constant for that infinitesimal, and so the amount of work is just the amount of charge we add, the tiny amount of charge. This is the beauty of integration in calculus. It allows us to examine a time-variant situation. We just say, all right, we can construct dq to be so small, because remember, v depends on q, right? We just see that up above. But we can fool Mother Nature briefly if we say we're going to make this a small instant of time. And basically, we do that by saying a very small amount of charge. So we assume that it stays constant while we're doing that. So, but we go back to our original definition, and we plug it into our infinitesimal. That's nice because now the dq, the variable of integration, what did they call that? The infinitesimal is the same as the function in there. And this is how you arrive at the energy stored in a capacitor. For us, the idea is that as you keep adding Q, it gets harder and harder. That's the takeaway. And that's why we need this integral to get this answer. See, with the resistor, the amount of voltage and the amount of current are only proportional to R. And in here, it seems like, give me a minute. What's the difference? Oh yeah, it has to do with when we construct this equation here. Because as soon as we add some Q, the voltage changes. That doesn't happen. I'm not explaining it well. I'm starting my it's better, but I'm starting my headache from my implant drilling. I talk to the doctor on Friday. I'm going to bitch and moan. 2 weeks. I shouldn't still be like this, sir.
The final equation, the final work equation considered steady state again?
Yes, correct. Okay, it's a great question. When all is said and done, that's what you end up with. It's not obvious, but what happens is that it means that as you get up there, the capacitor gets full, it's harder and harder to put more charge into it. And that's reflected in the graphs we're going to see of the time domain picture. And yeah, if you just take C equals Q over V, you can construct these. We are again not really going to use these equations. I'll post these slides, so don't rush around trying to write this all down. So here's and it's similar to that FET sim. So now we're going to examine what happens when you charge a capacitor. Now, we know that, and I've said it, R of a capacitor is equal to infinity, which means no DC. There's no steady state current. However, just as I finished saying, it takes more and more work to put charge in. When a capacitor is uncharged, it needs no effort to put a Q into it. So R, instantaneous, and this is also at Q, little q equals 0 ohms. So at the instant I close that switch, the resistance of the capacitor is equal to 0. You don't normally talk about the resistance of a capacitor, but that's exactly what's going on. Now notice we have the little I, the little q, they're both equal to 0. We are assuming the capacitor is uncharged and the switch is open, so there's no pathway for current to flow. Okay, so yeah, you want to sketch this circuit and make a few notes to yourself. But the picture itself basically shows the I equals 0, Q equals 0, and this R capacitor equals infinity is also useful later on. To note to yourself, when you look at an RC circuit, if you remember that, then it helps you right away to identify whether it's a low pass or a high pass filter. And I'll explain that when we get to chapter 2. But it's very useful to remember that. Okay, now I don't think things are going to change a lot on the next slide, but just yell at me to go back if you want. So I close the switch, and we see positive is at this left of the battery, so the current flows counterclockwise. And notice it's little I, once again, it's time dependent. Now you have a PDF I've posted, and it should be in this module, but it's in resources, and it's called RC Tutorial. I highly recommend reading it over. I stole the diagrams from it because they're much better than the diagrams that are in this textbook. So if we think about the voltage across the capacitor, there's two ways to think about it. We said that C equals Q over V. So we also know then that little v equals little q over c. When q is equal to 0, then there's no voltage across it. Remember, I said, though, at t equals 0, r cap equals 0. And also remember then, v equals IR. So if there's no resistance, you can't have a voltage drop. So the moment, of course, the voltage on the capacitor is 0 before the switch is closed. But at the instant I close it, it's also 0. And now you see that instead of going up linearly, it plateaus because it takes more and more work to squeeze in charge. At the beginning, the charge flows in quickly, and then it goes slower and slower. Now, this document was written by engineers, for engineers, RF engineers, and so this document, this graph reflects that important shit you need to know. So the time constant is the resistance times the capacitance, and it has to be ohms times farads. So you have to be careful about microfarads. You got to well, it's simple to just put, if it says 6 microfarads, then it's 6 times 10 to the negative 6, right? And that will come out in seconds. And then you see that the x-axis is in time constants. So the half-life is 0.7. It's 0.7071. And then the one half-life is when it's 1 over E, the 63%. You're going to deal with 63%. That's on your oscilloscope screen. There's dotted lines, or some of them have, maybe not all of them. I'll double check. But there's ways around it. And then it's generally considered after 5 time constants, some people 6 time constants. Because if you think about it, as an asymptote, it should take an infinite amount of time for it to charge. But that's Zeno's paradox, right? Achilles versus the turtle. If the turtle starts halfway, and each of them goes halfway each time, Zeno can never beat the turtle. Achilles can never beat the turtle. But that's presuming that you could, at a certain point, half the distance is smaller than the two objects, right? So in practical terms, of course Achilles beats the turtle. So we generally accept 5 to 6 time constants as the time that it's fully charged. So what we are going to do, we're going to be asked to look, and on your many oscilloscope screens are something like this. I believe it's 12, and I thought it was 63. Maybe it's 72 now that I'm saying it out loud. But anyways, what we want to do is we want to set up our oscilloscope so we can time how long it takes to get to this 63% line. So that's a side note to yourself. And this is the one time that the variable setting on the volts makes sense. And I'll go over this again, so don't sweat this. I just have I have this graph. So what you do on your oscilloscope is you set it up so the graph you see starts and plateaus on two lines. You can imagine if you're clicking it, it's never going to work, right? So you use the variable voltage. And then you know the delta V here, and you just figure out where is 63% of that, and then you slide this back and forth and pick up a convenient, I'll show you. Just giving you a hint right now. Anyways, the current, now notice also the mathematical form, 1 minus, because you want it at t equals 0, then this quantity is 0. Hopefully as physics majors you've seen this any number of times. Then the current, again, R cap at t equals 0 equals 0. So this one here is, they use V of S. Our original was the EMF symbol. So V of S is the supply. So the current, the instantaneous, well actually, this, they put a little I here, but this is I sub 0 generally called, the start current. I sub 0 equals V of the power supply divided by whatever R in the circuit, which is not R cap. If you didn't have a resistor, it would be the resistance of the wires. So no, you can never get infinite current. Your power supply can't supply it anyway. And it's the same markers. These are nice to memorize. Half-life 0.7, the 1 over E is 1, time constant, that sort of thing. That's all in that document. Okay. So now, how do we discharge it? Notice that now the capacitor is fully charged. The current is 0. The switch is open. Notice that I used to have the battery here with the plus. So this end of the capacitor is plus, the left side, right? Because that's where the current flowed in. So now when I close the switch, notice that, and I don't understand this, they got this wrong. The current goes the other way. Ooh, I forgot to fix that. Because the current's going to go plus to minus. So the current actually goes in the opposite direction. That's weird that that's wrong. Okay. So once again, we have our graph. Now this is voltage. So instantaneously, we see the capacitor's voltage, as it's full up, which also is equal to the supply. Although, remember, the y-axis here is voltage on the capacitor. And strictly speaking, I suppose it should be a little v. But even here, they use capital V. if you do the calculation, like this is how flash bulbs work in your cell phone. And if you've ever, I don't know why they do this. They like flash, electric flash for fancy cameras. They whine when they build up. They use that in science fiction movies for their pistols, right? Even in the Star Trek, when they flip them on the Star Trek Voyager, is it? Or no, I was watching Picard, right? It's great. They flip their phasers on and they whine, so it gets real deadly. Like, but anyways, what they do is you have a battery charged to capacitor. It may take some time because the terminal voltage of the battery, but once the capacitor is charged, it can deliver a big hit of voltage and current, and that's how you get a flash, even though the battery of your phone isn't that powerful. Batteries can't produce as much current as capacitors. So one of the big uses for capacitors is to trigger nuclear weapons. That's why, and photo flashes, right? See how the two are similar to each other. This is why the CIA they look for they watch companies that produce these big capacitors. They're used for other things, but if they notice that orders of big capacitors are disappearing, they kind of want to figure out where they're going, because the reason is because one of the simplest ways to make a nuke is to take a bunch of trapezoidally shaped pieces of uranium-235, and then you put a stick of TNT on each one. This is one of the original bombs that was dropped on Japan. Whoops, TNT, not I. And the thing is, you've got to deliver, they have to all explode at the same instant. And so one of the ways you do that is to have a capacitor instead of a battery, because it can deliver current, such a strong current, that the threshold to set off the blasting cap is reached very quickly, even if one of the ones on the other side, the voltage drop across the wires is a little too high. So these would be, they're shaped into a ball, a spherical shell, and then the TNT goes off and the uranium is slammed together, and you get, the density becomes high enough for a chain reaction. See, now you know how to build a nuke. Okay. What do we got? So we're going to try and look at this, right? So I'm going to fire up you're going to do this. Now, the thing is, I used to know what values to use here, and I forgot what values I have here, but I think you can put, say, a 1 to 5K right here, and then I would try out a 0.1 microfarad, maybe down to as much as 0.01 microfarad. So this is 100 nanofarads. That's 10 nanofarads. And see what happens. You can calculate the time constant. So let's take a look at what this would look like. And notice that the square wave takes the place, the square wave takes the place of this switch. Okay, so let's turn them on. We'll set them at auto for the time being. And there's so I have this circuit on my breadboard. And so I have my scope probe number 1 is here in, and then number 2 is over here. So this one, that's the blue, and that's the red. My traces on my oscilloscope. And at the moment, we've seen this before. I simply am looking at a sine wave. And you notice there's no phase shift, so I'm at the capacitor. This is a low enough frequency, right? That's funny. This is a kilohertz. Let's see what happens as I go up. So in this case, it's the resistance is going to go down. The output should go higher, right? Let's see. Let's get the frequency really low. So the resistance of the capacitor goes up, and one thing I have to do is I have to fix the, I don't want this to change. I want that to stay a fixed voltage, peak to peak. It's just like turning the voltage knob. So now the red trace has stayed the same. So now the resistance of the capacitor is very high compared to the okay. This is a low pass filter. So now the output. Okay. Now here's how you tell the difference quickly. The one on the right is a low pass a high pass because it won't pass DC. This is a low pass filter on the left, but I'll get back to that. So that means that at low frequencies, I expect no effect, and then if I go up, I should start to see the output crashing. And that's the blue, and I think we've already seen that happening. Now the red is the output. Okay. So now we're at 10 kilohertz. I'm surprised I haven't seen it shift any yet. So I must not be seeing what I thought I was seeing. Give me a minute here. Maybe I changed this. So I'm going into the resistor. I just don't understand why we're not seeing the red go down. It could be that, oh, there it goes. It's very high frequency. I'm up to 240 kilohertz, so that's way, you guys don't want to have to deal with that. And now we see the phase shift. Now, does everybody remember, do you guys know what a Fourier transform is? And so you know that a Fourier transform says that you can take any number of sine waves, add them together, you create any other waveform. So if I want to create a square wave, how many sine waves do you think you need? Infinity. Oh, you know that, right? Does everybody know that you need an infinite number of sine waves to create a square wave? Ah, okay, but that's one of the reasons sometimes we pulse things with a square wave, because then it's like we're giving it a multi-frequency pulse. And the way to think about it, and remember, of course, you're summing together sine waves, but of different wavelength. So we're trying to recreate, we want to make a square wave. So what we need is shorter and shorter wavelength to get us, and they add up to get into that corner. So as you get more and more sine waves, then you have something that looks like this. And the more you add to it, the more you square out the corners. So the reverse of that is that when you pulse something with a square wave, you're hitting it with all frequencies. So when we use a sine wave input, we're only hitting it with one frequency. It's not as critical to understand this, but what I'm about to show you. But the point is that you see how the capacitor is having an effect at the higher frequencies, right? And that helps you understand now when I switch this thing over to a square wave, that we see that. Isn't that cool? Now, when you look at chapter, and I have that illustration here, and notice the square wave is rounded off a bit. This is, well, 274 kilohertz. This has to do with there's a little bit of stray capacitance in the probes and such, and the circuit itself. You'll notice that I have that here. So I'm going to just show you these conditions that you see right here. So this is the first thing they want you to do. Oops. So you can adjust the time knob. So now I'm twisting it to the right. In your case, now I can lower the frequency here of the square wave. Now notice what's going on here now. The fun part is in this curve right here. That's where the time constant is. So you want to set this thing up so you can see that. And my circuit here is way too high of a frequency. And you notice how it's a back and forth. Now notice the plateau region is disappearing, right? So we want to have that plateau region just so we know we're not fooling ourselves. So that looks about ideal right there. Now, we want to see about measuring the time constant. So in my case, I have this thing. You can also either use the variable voltage on the oscilloscope, or you can change you have an amplitude knob on your function generator. So you can also change that. You see how I'm moving the red guy up and down? Because the ideal situation was when you have the capacitor, the voltage across the capacitor looking like this, starting on one line and then another. And then you can calculate what's the 63%, and then you move this thing. Let's see, how do we move this left and right on this screen? See, oh, that's not cooperating with me. It's moving the time down below. Well, anyways, what you want to do then is you figure out where is the 63% supposed to be, and then you slide this thing around. Well, we'll have to do it in real time. This is not a good demonstration because I can't do it. All right, so let's take a look here. We have high pass, low pass. Maybe this is not the time yet. Let's look at the text. How do we measure? Let's go back to the book. So first they want you to try to measure the time constant. Then we want to try and measure the output impedance. Oh, and just to finish the story here. So if I now switch and measure the voltage across the resistor, then I'll be able to see the current. And why is it, it's ringing like crazy. Okay. Oh, I see. No. Oh, did I? Give me a minute. No, I didn't set this up right. I just turned it into a high pass filter. I changed the type of filter. Oh well, I screwed up. I had a meeting with some new group I'm working with that went from 12:30 to 1:30, so I didn't have the time I normally would have had to show this to you, to set this up for you. I'll set it up at some point and show you. Okay, so it says in the textbook that, and let's get this to fit with, here we go. Measure the climb, yeah, he talks about it here. There's percent markings, you should have them on there. Okay, how will you know if the effect of R is rather than some combination of R? So it says to keep the frequency down. So that means that at this point, the capacitor will have a high resistance. I would have thought you'd want the capacitor to have a low resistance, so you're only measuring the, because what will you see here? You'll know, well, let me go back and see my notes. He doesn't do a good job of explaining this. So what we'll do now is I'm going to turn you loose, and get started and see if you can reproduce this traces here. Make sure you're writing down what you did and you're sketching your screen. And then when it comes time to do this, well, of course, you may need me to help you to measure the time constant. You're going to know your values. Make sure you get them, put them into the magic meter and get the exact values. And then we'll see if we can measure the same time constant. And I'll just come and sit with you, and maybe people that are nearby can watch over our shoulders too. And then the next step is this differentiator. They give you the parameters. What you're going to find is that these things, as he says in the notes, they don't always work. They don't work at all frequencies. But for now, I just want you to write down what you observe. And then on Thursday, I'll go back over the explanation that he has in there. Because at the moment, I just don't want to, I probably was talking for an hour, right? Looks like it's and that's about as much information as we can absorb at any one time. All right, so have at it. And when you get to these parts, if you're totally confused, then you call me over. All right. I'm going to turn the lights back on.
So we're just trying to recreate
I had a feeling that
spillway.
when you don't have any skin in the game, like a grade, you're just not showing up.
Oh, that's pretty easy.
You got him a grade. Oh, hell yeah. So that gentleman, that's Juan, isn't it? The guy who's missing? Yeah. I get the feeling we're not going to see him anymore, unfortunately. Hope he's okay, but he has an hand. Oh, I can't tell you that. And then I think this is Michael, and he's got a dentist appointment. So, oh, what's that? You're an A1, aren't you? Yeah, there's more. Is there more than one? No, what? So do we know the person that's absent? Oh, wait a minute. Nobody's absent, right? Yeah, I'm sorry, Guillermo. Oh, I'm sorry, Juan. But who was absent in this third row last time? It was you. Oh, I'm sorry. It was okay. I'm sorry. I'm really bad at names. I'm getting there though. We got Jordan, Jorge is there, Guillermo, and Christopher. Right, and I'm pretty sure it's Michael, and you are Francisco, and then Kevin's. Got that. All right, I'm getting there. All right. So the only part, we have Michael and Guillermo. I hope Guillermo's okay. Very good. Let me take care of that first, and then, just so I have it down. So I don't know, I know in the lab classes, they like threaten you with failure if you miss 2 classes. I don't think I'm required to do that, right? I mean, you just gotta keep up, right, and hand stuff in. Remember, guys, hand stuff in with some sort of reasonable effort.
So this is your setup for it.
Oh, yeah,